Okay, we'll start with this numerical. Now the numerical says that there are two shafts here, one hollow shaft and a solid shaft, and we need to find out the ratio of the maximum power transmitted. So ratio of the maximum power transmitted to hollow shaft divided by solid shaft. So we know that P, let me say PH stands for the power transmitted by hollow shaft divided by the power transmitted by the solid shaft. Okay, I'm taking this ratio because power transmitted by hollow shafts are definitely more than solid shaft for the same mass. So definitely this value would be more than 1. It would be more than 1. But how much it is, we need to find in this numerical. Okay, so we're supposed to find it. So here we know that the formula for the power P is equal to how much? P is equal to, now what is the formula for power? 2 pi nt by 60. So 2 pi nt by 60 is the formula for the power. So if it is for a hollow shaft, it is like 2 pi nt by 60 for hollow shaft divided by 2 pi nt by 60 for solid shaft. Now here what and all will cancel out? What and all will cancel out here? So 2 pi by 60, 2 pi by 60 they will cancel out, and what you are left with is n of hollow shaft, T of hollow shaft divided by n of solid shaft divided by T of solid shaft. But I think something is given in the numerical here. If something is given in the numerical, that we need to find the ratio of this power transmitted when both of this have the same mass, same material, same length and same speed. It says both are running at the same speed. So therefore you can say that this will cancel out. The speed of the hollow shaft and the speed of the solid shaft will cancel out. So therefore I can say that the ratio of the power transmitted PH by PS is nothing but the torque ratio. It is a torque ratio. Okay. Now, once we know this, we again go back to this formula for the torsion formula. So torsion formula is what, man? Now, what's the torsion formula? Tera towel, ganda theta, jaldi ring lagao. So this is how we remember. So we are worried about this first part of the equation. If you want this T, the torque, then this is actually tau into Jp by R. Of course, you call this as Jp or J, whatever. So this is the equation for the torque. So that means this is the shear stress in the material. This is Jp for solid shaft or the hollow shaft. Now what is the formula for Jp? Pi d to the power of 4 by 32. So you know that formula. So R refers to the maximum radius. So you can know it for hollow shaft and the solid shaft. Before we go ahead, we have one thing to say. It says that it has the same mass in the same material. Same mass. That means this hollow shaft and the solid shaft have the same mass. Same mass. So that means that its weight is same. Okay. So I should have said mass and weight here. So please don't confuse. And when I say mass, it is the same weight of this. So when I say same mass, so mass of the hollow shaft is equal to mass of the solid shaft. So how do you find the mass of the hollow shaft? Now what is the formula for the mass? Mass is volume into density of hollow shaft is equal to volume into density of solid shaft. solid shaft. Okay. Now here density, it says it is same material. Same material means density of this and this is also same. Hollow and solid is same. It gets cancelled out. It gets cancelled out. So I am trying to actually equate. Okay, I am writing this again here. I am trying to equate the equation. Volume of the hollow shaft is equal to volume of the solid shaft. Solid shaft for the same length, because length is also same. Okay, volume is nothing but cross-sectional area of hollow multiplied by length is equal to cross-sectional area of solid multiplied by length. Anyway, this length is also cancelling out. So basically I am trying to equate this hollow to this solid. Now here basically I have two shafts here. Hollow shaft, which is actually has an external diameter is how much? It is given that the diameter of the solid shaft is 150 mm. The solid side is 150 mm. The solid side is 150 mm. But this hollow side is no. What is the external diameter? External diameter is 250. External diameter is 250 mm. This is 150 mm. This is 150 mm. The weights have to be same. So I should find this di. Okay. So for that, what I do? I go back to this. I want this space, so I am trying to write here. So the cross-sectional area of the hollow shaft. So what is the formula for the cross-sectional area of a circle? Pi d square by 4. Area, cross-sectional area. So this is d naught square minus di square is equal to pi by 4 into d square. Okay, and therefore now I can write this as I am writing ulta like this. So here pi by 4 cancels out. What is actually d naught here? 250 square minus di square, which I don't know. Here this is 150 square. All these are in mm. So I find this di now. So using this I find di. So di is 250 square root of 250 square minus 150 square, which I get it as. So can anybody say what's the answer? 200. So I get this internal diameter as 200. So that means if external diameter is 250, internal diameter will be 200, then the mass of this will be equal to the mass of the solid shaft. Okay. Now we are supposed to find out the ratio of the power, which is the ratio of the torques. So what we will do, we will try to substitute the ratio of the torques here. So we have done up to this point where we have found out that this external diameter is, this internal diameter is 200. Is it visible up to here? Okay. Now we know that the torque is given by this formula. So the torque of the solid shaft divided by the torque of the hollow shaft. The torque of the hollow shaft divided by the torque of the solid shaft. So that is given by tau Jp by R for hollow shaft divided by tau Jp by R of solid shaft. Okay. Now it says that the material is same. metal is same means if it is aluminum, if it is aluminum here also. Aluminum here, steel here, steel here. So that means their shear stress, that is the maximum shear stress that can take is same. The value of shear stress that this metal can take is same. So therefore, since metal is same, the shear stress will cancel out. So I am now cancelling out this hollow shaft and solid shaft shear stress because they will fail at the same shear stress. So maximum shear stress for this, if it is 150, for this is also 150. So it has to cancel out. Okay. So we are only left with the geometrical parameters here, which is JP, which you already know what it is. But you know that JP is equal to, JP for any solid shaft is equal to pi d to the power of 4 divided by 32. But if it is a hollow shaft, it is, if it is a hollow shaft, then JP for hollow shaft, for solid shaft it is okay. For hollow shaft it is pi by 32 into d naught to the power of 4 divided minus d to the power of 4. Okay, so I am substituting this now. So here this becomes for hollow shaft, this is pi by 32 d naught to the power of 4 minus di to the power of 4. So that is JP divided by R. R is actually what? R is actually the distance from the center to the extreme fiber. So what is this R? So what is this R in terms of d naught? It is d naught divided by 2. So this is d naught divided by 2. Okay. And for the solid shaft, it is pi d to the power of 4, pi by 32, d to the power of 4. D to the power of 4 divided by R. R for solid shaft is distance from the center to the extreme fiber. R is actually d by 2. It is d by 2. So what and all will cancel out here? Please check. What and all will cancel out to make this. So pi by 32 will cancel out. This is gone. And then this 2 and 2 will cancel out. It is in the same, this one. And then what you are left with is d naught to the power of this divided by this. So this is d naught to the power of 4. D naught to the power of 4 minus di to the power of 4 divided by d naught. Again here divided by this d, and this d will become d cube. Okay. So once you have done that, then you can substitute these values here. You can substitute the values. You can substitute the values of this. So let me write this here. Substitute the values here. What is actually d naught here? 250. So 250 mm to the power of 4 minus, so 200 mm to the power of 4 divided by d naught, which is 250 mm, all divided by d3. So how much is d? 150 mm cube. So this divided by this. So this is actually giving what? This is actually giving the ratio of the power transmitted, which is actually the ratio of the torque transmitted, basically. So power or the torque, the same. Okay. So now what is this values, man? Can you tell me? 2.73. What does this mean actually? Which means that if you call this as power divided by pH HS, so pH divided by PS is equal to 2.73 means you can write this as like this, which means that the power that could be transmitted by this hollow shaft is 2.73 times the power that could be transmitted by solid shaft. For the same mass, same speed, same length, same material, everything is same. Then why are we not going for hollow shaft? then why shouldn't people go for hollow shaft? People should definitely go for hollow shaft, but the only problem is how to manufacture a hollow shaft is, I think, now for a solid shaft you can actually forge it easily and it actually densifies and it becomes a solid shaft, but to make a hollow shaft it's not easy. Okay, you need to extrude it. I think the processes to make hollow shafts are difficult. So therefore, usually hollow shafts are preferred where you are transmitting larger torques, okay, over longer distances. For this front wheel driven front engine cars, like most of these sedans and hatchbacks, okay, where the length of the shafts are quite short, we usually use solid shafts. Okay, so hollow shafts can definitely transmit more than 2 times of the same power. You can, I think we have given some dimensions here. For this dimensions it was 2.73. Maybe for other dimensions it could be other number. But it's not a standard. Now what is the ratio of power? So that means you need to know the dimensions of this solid and hollow shaft, only then you can say this. So you can write a comment below. For the above dimensions, hollow shaft can transmit what? Hollow transmit can transmit what? 2.73 times of 2.73 times of what? Power. 2.73 times of power compared to a solid shaft.